Hey guys, today we are covering Chapter 5. We're going to do sections 1 and 2. They're both a little quick, dealing with the periodic table. Please have a periodic table handy as we go throughout this. We have several definitions that you're going to need to write down, and most of this is just straight up informational. There is a little bit of application going on, but memorization. So Mendeleev, he's one of our scientists. He noticed that when you arrange the elements in order of increasing atomic mass, certain similar chemical properties appeared at regular intervals. This is where the term periodic is going to come into play. So again, Mendeleev, he arranged them in order of increasing atomic mass. And these were all of the elements that had been discovered at that particular time. These repeating patterns are periodic, and he created a table with these elements to show similar properties were being grouped together. We're going to go take a look at the first periodic table that was created, and Mendeleev is going to be given credit for that first periodic table. There are some things I want you to know about the first periodic table created. Again, it was created by Mendeleev, but notice here our elements. If I am looking at, say, these right along here, notice that all of those, if you're looking at your current periodic table, they are in a row together, so a period, but notice they are vertical here as a group, so his groups and periods are backwards compared to what our current periodic table is. So they are switched around as far as vertical and horizontal rows. And notice we don't have anywhere near 118 elements. Those numbers at the end of the symbols are going to be the masses that were known at that time. So we are missing large sections. If I look at the large sections that we are missing off of this periodic table, we are missing, see if you can figure it out too. You're missing your noble gases. Again, they're all gases. We are talking back in the 1800s here, so it's really hard to not only test gases, but knowing where to get some of these gases to test. So your noble gases are missing, and when they were first discovered, you know that they were considered to be inert or unreactive. The second and third big groups that are missing are the Lanthanides and Actinides. That is our F block. And we will talk about all three of these groups today, their discoveries, things like that. So those are big groups that are missing. And one other thing I want to point out on Mendeleev's table, we have some question marks. There are several. But here's what Mendeleev is given credit with. Once he put his periodic table together, and he was able to say, you know what, the way I have it grouped together based on increasing mass, you're going to have similar properties that appear close to each other. So I see a question mark here at something that he suspected had a mass of around 45, so that's between 40 and 56. And then I see two others up here. So we had zinc with a mass of 65, arsenic with a mass of 75. He predicted that there were two other elements that belonged in there, one roughly a mass of 68, another one a mass of 70. So even though he did not discover those three elements, he at least was able to narrow down for different scientists, okay, these are some masses, and you know what? Whatever has a mass of 45, its properties might be similar to calcium above it. And if I'm looking, ER is not the symbol we use anymore, but the element that has a mass of 56 is iron. And again, I'm looking at my periodic table. Iron's mass is close to 56. So the element that falls in there should have some properties like a metal, because those two are metals, similar to those two, but the mass is going to be around 45. So if I go back and I look at my periodic table right now, the element that has a mass really close to 45 is going to be scandium. So scandium was discovered later. Getting back up to the other two, a predicted mass of 68 and 70. They fall between zinc and arsenic. Well, the two elements that now fall between zinc and arsenic are gallium and germanium. And gallium's mass is going to be close to 70, and germanium's mass is going to be close to 73. So there you have those two also. So again, know something about Mendeleev's periodic table. A lot was able to be discovered after his first arrangement. This is just some quick information on those three elements that I was telling you about. You've got gallium, scandium, germanium, the years that they were actually discovered, and these are going to be, 1871 is when Mendeleev put that periodic table together, so you can see this is going to be a few years, up to about 15 years after what he did. We had predicted properties, what Mendeleev at least predicted, and then once those elements were actually discovered, there's the observed properties once they were discovered. And you can see that, yes, those properties are going to be very similar to what was predicted based on the arrangement of the periodic table he put together and what they knew about the elements that were close to those. So again, Mendeleev is given credit with the first periodic table, 1871. His were arranged according to increasing atomic mass. Now in 1911, we have got another scientist named Moseley, and Moseley said, you know what? He thought that the elements fit a better pattern if they were arranged according to atomic number rather than atomic mass. So he arranged a new one in 1911 based on increasing atomic number instead of atomic mass. I want you to go back, look at your periodic table, make sure we are on the same page, knowing where the atomic mass and atomic number are. So as I'm looking at this periodic table here, I'm going to highlight a couple of things. I'm just going to go in and we are going to pick out, how about hydrogen? No, hold on. I realize we need a little bigger so we can actually see some of these numbers. So I'm just going to pick iron that is right here in the middle. So the whole number that's in the element cell, the 26, that is going to represent the atomic number. Again, as a refresher, atomic number is the number of protons, and if it's a neutral atom, also the number of electrons. And then that decimal value that you see at the bottom, that is going to be its average atomic mass, so an atomic mass or atomic weight of all the isotopes of the element. Please make sure you know where to find atomic number or average atomic mass for any element if you're looking at the periodic table. And you have another definition here, the periodic law. The periodic law says that physical and chemical properties of elements are periodic functions of their atomic numbers. So again, the word periodic there is just a repeating pattern. So if I were to put it in other terms, the chemical properties are a pattern based on atomic number. If you put all the elements in order of increasing atomic number, these patterns of properties will repeat themselves. So we're going to look at periodicity. Normally I draw this out for the kids, but this, I want you to write both of these in your notes. We are looking at group 18 there to start with, the one that is here on the left. These are the elements within group 18, helium through radon. We're not going to element 118. But there's their atomic numbers right here. And if you find the difference means subtract. If you find the difference in the atomic numbers, there is a pattern. 8, 8, 18, 18, 32. And you will find that this pattern, or even parts of this pattern, repeat throughout the entire periodic table. So that's group 18. Then we head over here to group 1. They are leaving hydrogen off because period 1 is very short. So group 1, lithium down through francium, there's their atomic numbers. And then if you subtract the atomic numbers there, again, same repeating pattern, 8, 8, 18, 18, 32. If you go and you pick other other groups, groups 2, 13, 14, 15, you'll see this pattern. Even if you pick groups within the D block, you're still going to see the patterns of 18, 18, 32, and 32, especially if you add on all the newer elements that are at the bottom. So again, that is a repeating pattern. Hopefully you're looking at your periodic table, and maybe you can also recognize that 8, that's how many elements are in period 2. That's how many elements are in period 3. These 2, that's how many elements are in periods 4 and 5. That's how many elements are in period 6. And again, with all of our other new elements, period 7 will also have 32. So that pattern does mean something. And again, periodicity refers to a repeating pattern. And those patterns appear in the periodic table. And here's your definition for periodic table. It is an arrangement of elements in order of their atomic number, so that elements with similar properties fall within the same column or group or family. So elements with the similar properties fall within the same group. Moving on to section 2. So this is chapter 5, section 2. We're going to start to get into some more terminology here. Again, some of it should be a refresher for you, but write down what you need as you need it. Elements are arranged vertically in groups. So elements in their vertical columns are in groups. This is where you have your similar chemical properties. That does not so much appear in a period. The horizontal rows are called periods. The length of each period, which is what we just looked at with periodicity, is determined by the number of electrons that can occupy the sublevels that are being filled. And we will look at the sublevels being filled. We will come back to this one right here and show you the numbers and how they work with those sublevels. And then the last one, the periodic table is divided into 4 blocks. You are familiar now with the S, P, D, and F blocks. And again, it's determined by what electrons are being filled where. So hopefully you remember most of that. If not, get it written down. When you come back after we go through all this, I will be giving you a periodic table, and we're going to be coloring it up with the main groupings on here, distinguishing some other groups, but definitely between our S block, D, P, F blocks. And we're also going to break down some of the groups within those blocks too that have their own special properties. Group 1. So now we're going to break down some specific groups. You need to make sure you bullet point these different ones. We are going to go through properties of certain groups and make sure you get the details of each one. So group 1, they are known as the alkali metals. Here's all of the alkali metals, but if you're looking at your periodic table, in group 1, we don't include hydrogen, but lithium down through francium, every single one of those. In their pure state, all of the alkali metals have a silvery appearance and are soft enough to be cut with a knife. We're also going to go look at a video right now of their reactivity. So as you move down group 1, we're going to look at lithium through cesium. We're not going to look at francium in the video because francium is radioactive, but lithium through cesium, all of them. As you move down the group, they become more reactive.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
Okay. So as you can tell from the video, yes, definitely as you move down the group, the reactivity does become more aggressive with either the air or the water, whatever it is it's going to react with. So that is your group 1 alkali metals. Group 2 are known as the alkaline earth metals. And this is going to be beryllium through radium. They are slightly less reactive, than the alkali metals, but are still too reactive to be found pure in their pure form within nature. So alkaline earth metals is the special name for group 2. Hydrogen. We're going to bring hydrogen out by itself. Hydrogen is a unique element, and its electron configuration is 1s1, meaning it has the one electron. Even though it shares the same general configuration as your group 1 metals, I'm hoping by now you realize its properties are not like the group 1 metals. Yes, it is very reactive, but instead of it being a metal, we say it's a non-metal. It's actually in gas form at room temperature, so it has its own set of unique properties. There are several things you need to write down here. Again, hydrogen is a unique element. Its general configuration is NS1, and as you recall, that N references your energy level. So for group 1, their general configuration is NS1, and that's going to be its outer electron configuration. Since hydrogen is in period 1, that is why it has become 1s1. But if I were to look at some others going down that group, for instance, lithium, since it's on period 2, that would be 2s1. Sodium is on period 3, so that is 3s1. So don't forget, we're going to see that N pop up more. N references your period number or your energy level. So you can follow that on down through francium. Francium's on the 7th row or 7th period, so it would end with 7s1. So now for our group 2 elements, again, the alkaline earth metals. We have a general configuration here for these two, and that is going to be NS2. And again, helium is over there with part of group 18. It's very special, but because the highest occupied energy level is filled for helium, helium possesses its own special chemical stability. We said in the last chapter that stability can be created with a filled energy level, a filled sublevel, or a half-filled sublevel. Well, helium, once 1s is completely filled up, not only is the s sublevel filled, but the whole first energy is filled with just those 2 electrons. That's why it has that special stability and is put with the noble gases. But for anything within group 2, there is the general configuration, NS2. And if I look at beryllium, since beryllium is on the second period or second energy level, 2s2. If I go down to rubidium, rubidium is on the fifth period, so rubidium would end with 5s2. Again, the N represents your period number or energy level. Now we're going to do a little correlation between periodicity and electron configuration. So periodicity, electron configuration, and we've got three different pairings that we're going to look at here. Let me erase some of these stray marks. Period number. We've got how many periods on the periodic table? Hopefully you answered 7. That's for our modern periodic table. The number of elements within that period. On the first period, there's only 2 elements. Second period, 8. Third period, 8. I'm hoping you see this pattern emerge. And again, we have discovered or created the full length of period 7 now to incorporate all 32 elements. And that part I said, hey, we're going to get back to label. These are the sublevels that are being filled with electrons. And here we go. So period 1, the 1s sublevel is being filled. In period 2, you fill up 2s and then 2p. In period 3, you fill up 3s and 3p. And again, we're going to go do a little math just to correlate some of the things that we had seen earlier. An S sublevel can hold how many electrons? 2. A P sublevel can hold how many electrons? 6. So again, S sublevel, the 1 orbital can hold 2 electrons. A P sublevel has 3 orbitals. It can hold 6 electrons. So 2 plus 6 is 8. Same thing goes on there in period 3. Down at period 4, the first thing you hit is 4s. And as you move to the right, you hit 3d and then 4p. Same thing goes on with period 5. 5s, 4d, 5p. And again, that is all refreshers from the previous chapter. And if we do our little bit of adding again, an S sublevel can hold 2 electrons. P sublevel can hold 6. How many electrons can a D sublevel hold? Hopefully you remembered those 5 orbitals can hold 10 electrons. So 2 plus 10 plus 6 is 18. And then down in period 6, we start off with 6s. We move to 4f, 5d, 6p. And again, you take the 18 we had previously, F sublevel can hold 14 electrons. 18 plus 14 is your 32. And then we have the same thing going on within that last one. Again, all of this was stuff we're just correlating from the previous chapter, putting it all together for you so that you know how some of these numbers are coming in and working together. So please be aware, period number of elements, it's based on the sublevels that are being filled. So again, one is based on the other so that those numbers start to make a little more sense. Okay, we're going to be working out several sample problems as we go through these right here. Now this does say without looking at the periodic table, but for this test you'll have a periodic table. It wants you to identify the group, period, and block in which this element with that noble gas configuration is located. So here's the thought process I would be going through to try and figure this out. So we have Xe6s2, and it wants the group, period, and block. Sorry about that. So the easiest thing to look at here is going to be the highest occupied energy level. So this right here is my highest occupied energy level. That is period 6. So highest occupied energy level, that is period 6. The only block even represented here is the S block. So as I look at that, that's the only sublevel represented, so my element is in the S block, and it is the second group over in the S block. Well, the S block only has groups 1 and 2, so it must be in group 2. So 6th period, S block, group 2. You should be able to do that without a periodic table at this point, based on what you have been taught. If I asked you to identify the element, I would definitely want you to have a periodic table to be able to identify the element now. And then the other one, without looking at the periodic table, write the electron configuration. And this is just going to be that outer generic electron configuration for an element that is in group 1, 3rd period. So the first thing I'm thinking is, okay, group 1 falls in the S block. My generic configuration is in S1. Since it's group 1, now I just fill in what the N value is. And since I'm looking at it, the 3rd period, that is our value of N. So that is going to be the outer configuration. If you're looking at a periodic table, you should definitely be able to fill in all of the stuff that comes before 3S1, which is 1S, 2S, 2P, and then we would end with 3S1. Now we're moving on to the D block. So for the D block elements are typically called transition elements or transition metals. These are metals with typical metallic properties. The D sublevel does first appear on the 3rd energy level. Even though that is the 4th period in the periodic table, remember, for the D sublevel, it's N minus 1, which 4 minus 1 would be 3. Okay, here's a new problem involving the D block. So it gives you the noble gas configuration for an element. Again, it says without looking at the periodic table, it wants you to identify the period, block, and group where this element is located. So period, block, and group. Now, if you recall, the order of filling, 5S in this case would fill up before 4D. And they also give you one of the exceptions. Okay, so this has been switched around, but I'm going to show you if you just have a D and S sublevel listed at the end, no P sublevel at the very end, so just D and S. Remember, S does fill up first in the periodic table, then D. So S and then D. So if those are the only two appearing at the end of your configuration, you have to have something within the D block. So in this one right here, the period is going to be the easiest thing to identify because as I look at this, you're looking for the highest occupied energy level. The highest occupied energy level is 5, so this is on the 5th period. The block is the next thing I would look at because, again, you have to recognize D and S are flipped around to get the lower energy level number 4 first, then the higher energy level 5 afterwards. So this is the D block. This is the D block. And now you're looking at group. Once you recognize it is D block, the absolute easiest thing to do at that point is to add your electrons in S and D. So add up electrons between S and D. 5 plus 1 is 6. So that is group 6. Now, if you recall from the last chapter, we said that there are exceptions to the order of filling, especially for group 6 and group 11 out of the D block. They'd like to pull an electron out of S, put it into D, and in this case, it gives D a half-filled sublevel, which creates stability. That's why you just see the 1 electron in S. So that is for the D block. Now moving on to our main group elements. Main group elements are any element in the S and P block. Any element in the S and P block. So we know the P block itself is groups 13 through 18, except helium. But when you get to main group elements, that's going to include your hydrogen and helium because they're part of the S block. So the P block, looking at properties of just the P block. It says it varies greatly. We have all kinds of elements going on in the P block. We have nonmetals in the right hand end. We have metalloids along the stair step. And then we also have metals in that lower left corner. So we have metals, metalloids, nonmetals all going on within our main group elements or within the P block. Now we're going to break that P block down. Again, the metalloids, you should know what your 6 metalloids are. Boron, silicon, germanium, arsenic, antimony, tellurium. Make sure you still have those. So we're going to break out group 17, which is there in the P block. Group 17, known as the halogens. That's fluorine, chlorine, bromine, iodine, and acetone. For our halogens there, they react vigorously with most metals to form the generic classification of compounds called salts. So group 17 with a metal forms compounds called salts. The easiest ones to pair them with are group 1 or group 2 metals. So group 1, the one that you are familiar with, Na, group 17, chlorine. Sodium chloride, that is table salt, but we have lots of other salts. I could do potassium bromide. Rubidium, fluoride. How about lithium iodide? I'm picking a lot of group 1 metals with a halogen. But again, any of those are called salts. This just happens to be table salt that you're probably most familiar with. And then with our metalloids, metalloids are semiconductors. They are located in the P block along our stair-step line. And then we do have several metals in that lower left corner within the P block. These are generally harder and denser than S block metals, but softer and less dense than your D block metals. So make sure you get that down as differences for those P block metals. And your P block metals, your tin and your lead fall within that category. Now, since we are looking at the P block, we're going to look at the generic configuration for N. It is NS2, NP, some number 1 through 6. So again, N represents your energy level. Notice the S sublevel is already filled with 2 electrons. So S does fill up before you ever get to P. And then in P, I've got it set up, or it's set up anywhere between 1 and 6 electrons because there are 6 groups within the P block. Let's go use this generic configuration to answer our next question. So again, it says without looking at the periodic table, can you write the outer configuration for a group 14 element in the second period? Group 14 element in the second period. So what we just had was NS2, NP, some number 1 through 6. You should recognize group 14 is definitely within the P block. So P block is any group 13 through 18. Our value of N, it's in the second period, so it must be a 2. This is also a 2. Again, this is for that generic configuration that we've got. In P, now we've got to pick some number 1 through 6. As I am looking at the periodic table, again, group 14. The groups in the P block are groups 13, 14, 15, 16, 17, and 18. Well, group 14 is the second group over within the P block, so that is going to have to be NP2 because it is the second group within the P block. That is your final answer for the outer electron configuration for an element in group 14, second period. Now we're quickly breaking down the F block. It is again it's wedged between group 3 and 4. They are in the 6th and 7th period. Again, some of this is a refresher for you in the 6th and 7th period. You have your lanthanides that are in the F block. They're in the 4F sublevel. They are shiny metals similar in reactivity to group 2 metals. And then the second row of the F block are your actinides, and they are all radioactive. So all of your actinides are going to be radioactive. Once you get back to class, we're going to take our periodic table. Lots of coloring is going to go on to get all of these different groupings out. So hopefully we'll have another visual for you to keep everything together.